Alright, thanks for watching, and today I would like to talk about a very deep result in linear algebra that is quite surprising. Namely, I will show that even though the row echelon form of a matrix may not be unique, the reduced row echelon form of a matrix is always unique. In other words, if you and your friend row reduce the same matrix to reduced row echelon form, both of you should get the same answer. That's why it's also a nice problem to ask on an exam, because it's easy to grade because everyone should get the same answer. So let me just remind you what the reduced row echelon form is. So first of all, a row echelon form is kind of like triangular form of a matrix, which has the following requirements. First of all, if there are any rows of zeros, they have to be at the bottom. And also, whenever think of it as the edge of a cliff, whenever you have a non-zero term here, which is called a pivot, everything below and to the left of a pivot has to be zero. For example, if this is a pivot, everything below and to the left has to be zero. So this is called a row echelon form of a matrix, and this is not unique because, for example, this thing, 2, 2, 0, 2, that is a row echelon form, but this is row equivalent to, let's say, 1, 1, 1, 0, which is also in row echelon form. Now, what is the reduced row echelon form? It further requires, first of all, that the pivots are 1. So all the pivots are 1. And everything in a pivot column has to be 0 except for a pivot. So basically everything strictly above and below a pivot has to be 0. But for example, this is also, those terms don't have to be 0, the ones that are not in the pivot columns. And I want to show you that this sort of description of a matrix is unique. Now, usually it's a very difficult fact to prove, and at least the book I'm using, I don't understand their proof, but I found this really beautiful proof online by Thomas Euster in Middlebury College. And actually, fun fact, Middlebury College is very close to Williams College, where I used to be for a year. So really, really cool. And they usually have math competitions between the two. Called, I think, the mathematical chicken or something. You get a chicken vase if you win that competition. So very cute. And how does the proof go? It turns out it goes by induction, because we want to do this step by step, and we'll do induction on n, which is the number of columns. So induction on n, and where a is m by n. Well, first of all, it's all about the base case. So suppose n equals 1. In other words, suppose A has only one column. Then here's the thing. There are only two reduced row echelon forms. Either it's the 0 column, and the only matrix which has this is the 0 matrix. So if this is the reduced row echelon form of A has to be the 0 matrix. Or if A is any other non-zero matrix, then the only reduced row echelon form is just 1, 0, 0, 0. Because if there are, first of all, if there's a pivot here, everything below the pivot has to be 0. And also, suppose you have some non-zero matrix, something like that, then you can reduce it to get something 0, 0, 0, and this becomes 1, 0, 0, 0. So in other words, any other non-zero matrix must have only this reduced row echelon form. So in this case, the RREF is unique. That's not the exciting part. The exciting part is the induction step. So suppose this is true for m by n matrices, or let's say for m by n minus 1 matrices, and let A be a m by n, be n by n. No. I know I'm apologizing. I am telling the truth, so it's okay. All right, in other words, so suppose you have a m by n matrix, something like that. And suppose, let's say it has two distinct reduced row echelon forms. Suppose you can reduce it either to B or C. But here's the thing. We know that it's true for m by n minus 1 matrices. So consider the submatrix just formed by the first n minus 1 columns. In other words, suppose you ignore the last column, then you get a matrix A prime. And same with B. Suppose those are the first n minus 1 columns, and those are the first n minus 1 columns. And you get B prime and C prime. Now here's the thing. If we row reduce A to get the reduced row echelon form B, the same process works to row reduce A prime to get a reduced row echelon form B prime. Because essentially what you're doing with this bigger matrix, you're just doing more work. You're showing it's true for a bigger matrix. So really you can just apply the same process and get A prime have RREF B prime or RREF C prime. But basically A prime, if you reduce row echelon form it, it becomes B prime or C prime. But here's the thing. A prime, B prime, C prime, they're smaller matrices. In particular, they're in the induction zone, which means we can apply our induction hypothesis to it. And the induction hypothesis says there's only one reduced row echelon form, which means the only way we can reduce row echelon form A prime to B prime or C prime is if both of them are equal. So by induction hypothesis. Sounds like a superhero movie. There can only be one. Well, there's only one reduced row echelon form here. So we do know that B prime equals C prime. And really the Optimus prime. And really the question boils down to, what about the last column? Are the last columns equal? Because if they are, we get that B equals C, which will show that reduced row echelon forms are unique. So the question is the nth column equal? So in view of contradiction, suppose B is not equal to C, which means somewhere here, some jth entry is not equal. So this means if this entry is bjn, there's some entry in the jth row that's not equal to the corresponding entry for C, because otherwise B would be C. Because we know that their first n-1 columns are equal. So bjn is not equal to cjn for some n. Okay, that's one thing, and we'll use that in a second. Now, here's the other thing. So, row reducing is basically just like multiplying by invertible matrices called elementary matrices. And in particular, row reduction preserves the null space, because whenever you multiply by invertible matrices, it doesn't change the null space. In particular, if you row reduce A to get B, the null spaces are the same. And also the null spaces here are the same. So what we get is that the null space of B equals the null space of A equals the null space of C. Because again, row reduction doesn't change the null spaces. So in particular, those two null spaces are the same. So let's pick a vector that is in both of the null spaces. So let X be in null space of B, which equals null space of C. And X could be the 0 vector. That is not a problem at all. So possibly X equals 0. Then, let's see what happens, and we'll find some kind of contradiction here. No, not quite. We will show something interesting. We'll show that if X is in the null space, its last coordinate has to be 0. Interestingly. Which is not quite obvious. Maybe it is for you. So because X is in the null space of B, Bx equals 0 and Cx equals 0. So in particular, B minus C, X equals 0. So we know that. On the other hand, what is B minus C? Or B minus Cx? Remember, B and C, their first n minus 1 columns are equal. Because, just showing you this picture again, here the 2 columns are equal, so if you subtract them, you just get the 0 matrix. And it's possible that the last column is not equal, so you might get gibberish in the last column. So, B minus Cx equals a huge 0, some junk times x, the vector x, equals whatever, bunch of zeros. And then, if you think of x as x1, x2, etc., up to xn, x1, x2, up to xn, and you multiply it, so maybe let me be more clearer with this last column. That would be b1n minus c1n, bjn minus cjn, up to bmn minus cmn. Amen, okay? And then, if you multiply those out, you get 0, 0, 0, up to b1n minus c1n xn. So you get b1n minus c1n xn, or bjn minus cjn xn, and then bmn minus cmn xn. And you know this is 0. But remember, so it's possible that a bunch of those terms are 0. But if you remember, we do have that one of those is not equal, because otherwise we would have B equals C. So for some of the, for some index j, we do have that bjn minus cjn is non-zero. So if we get bjn minus cjn xn equals 0 by assumption, and this is non-zero, this actually forces xn to be 0. Alright, because, and so in other words, any vector in that null space must have xn equals 0. So that's interesting even if you have the 0 vector. So that's not a problem. So what can we actually conclude? And therefore, what do we conclude? We conclude that the last column of B and C, they have to be a pivot column. And here's why. So, in other words, so last column of B and C must be a pivot column. Why is that? It seems kind of weird. So how does showing that null of B, if x is in null of B, then the last coordinate has to be 0. How does that show that the columns must be pivot columns? Well, suppose that the columns look like this. So suppose B looks like this, and the last pivot is a non-pivot column. In terms of what you know for linear equations, non-pivot columns, they correspond precisely to free variables. So in other words, what that would say is that xn is a free variable. So in particular, at least heuristically, if you want to solve bx equals 0, then the pivot columns, those are basic variables, let's say x1, x3, x5. And then it means that the basic variables, you can write them in terms of the free variables. So x would be equal to the following. It's equal to x1, x2, up to xn, which could be written in terms of the free variables. So minus blah x2, minus something xn, and then x2 would, let's say, be free, and then up to xn, which is free, which tells us that xn is a free variable, as I said. So the solution would be x equals to xn plus x2 plus any other variable. And in particular, if you choose, let's say, so xn times 1, that's very important, x2 times 1. In particular, if you choose, for example, anything else equals 0 but xn equals 1, then you would get a solution of the form x equals to whatever and 1. But we just said that any solution of bx equals 0 has to have that the last coordinate is non-zero, and has to have the last coordinate is 0. And that's why we actually get a contradiction with the assumption that it's not a pivot column, which means that the last column actually has to be a pivot column. All right, but here's the thing. What does a pivot column look like in the reduced row echelon form? It has to be of the form, first of all, the pivots have to be 1, and everything above and below the pivots have to be 0. So in particular, both B and C must have of the column of the form 0, 0, 1, 0, 0, 0. Now, it's possible that this 1 is in two different spaces. So it's possible that the last column of B is like 0, 1, 0, 0, but the last column of C is 0, 0, 1, 0. And we want to show, no, this actually doesn't happen. So claim the 1 in the pivot column must also be in the same row. Because suppose, just for sake of illustration, that B looks something like that, where the 1 is in the third row, 1, 0, 0. And C looks something like that, where the 1 is in the fourth row, 0, 0, 0, 1, 0. Fourth row. Then, remember, first of all, this last column is a pivot column. So everything to the left of it has to be 0. So that we already know. Now, remember though, we do know that the first, everything but the last column of B and C, which we call B prime and C prime, have to be equal. So if there are a bunch of zeros in the third row of B, we also know that there are a bunch of zeros in the third row of C. Okay, so far that's which is already a contradiction because we then get that the 0 row is not at the bottom. Therefore, we already get a contradiction, which must mean the 1 in the pivot column must be in the same row. And in particular, what do we get? We get that because both the last column of B and C must be a pivot column of this form, and the 1 is both at the right place for B and C, it really means that B and C must be the same. Because what do we know? We know now that B equals have the same last column, which is just a bunch of zeros and then a 1 and then 0, 0. And C also has the same last column with the exact same position of the 1. And by assumption, everything else is the same, which tells us that B equals C, which, if you want, is a contradiction with B not equal to C. So in other words, if you row reduce A to get two different reduced row echelon forms, that can never happen. Therefore, the reduced row echelon form of a matrix is always unique. And as I said, I like this proof a lot. It doesn't use very messy indices, just a little bit of intuition about null spaces and contradictions and pivot columns. Alright, I hope you liked this little fun video. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.